Hello. This is the lecture for section 3.3, graphs of polynomial functions. All right, let's start with reviewing intercepts. We call it the intercepts graph is where they cross the vertical or horizontal axis. All right, so on the vertical axis, we know that all the input or x coordinates are 0. On the horizontal axis, all the output or y coordinates are 0. Here we have this function p of r. That means the vertical axis is going to be p and the horizontal axis is going to be r, all right, instead of x and y. And as you recall, all of the points on the vertical axis have an r value of 0, right? And all the points on the horizontal axis have a p value of 0. Okay, so in other words, then if I want to find the p-intercept for this problem here, or this equation, this function here, if I want to find the p-intercept, I'm going to need to let r equal 0. Okay, so I'm simply going to be finding p of 0, which is pretty easy, isn't it? 3 times 0 to the 4th power minus 3 times 0 to the 3rd power minus 18 times 0 squared. Of course, that's just 0. All right, so that's telling us that the graph intercepts the p-axis at r equals 0, right? The p-coordinate, of course, is going to be 0 as well. I'm sorry, the r coordinate is going to be 0 as well because they all are on the p-axis. Ooh, these p's and r's are confusing more than x's and y's would be, aren't they? Okay, so that means the coordinates of this point is simply the origin. The p-intercept occurs at the origin. Now, to find the r-intercept, I'm going to do a little bit of algebra, right? To find the r-intercept, we have to let p of r equal 0, right? So we'll set that whole equation equal to 0 and solve for r. So 3r squared, 4th, sorry, that's 3r to the 4th, minus 3r cubed, minus 18r squared is equal to 0. All right, now I think the best way to solve this is, let's see if we can do it by factoring and then using the zero product principle, right? So we'll start with the greatest common factor. Looks like each of these terms is evenly divisible by 3r squared, so let's pull that out. And then what's left behind? An r squared minus r minus 6. And we can keep on factoring, so let's do that. 3r squared times that trinomial, r squared minus r minus 6, that's going to factor into r minus 3 times r plus 2. There. Now that we're fully factored, we can set each of those factors equal to 0, employing the zero product principle to find, we're going to find 3 r-intercepts, right? So either 3r squared equals 0, in which case r has to be 0, right? Because look, divide by 3, r squared is 0. Now take the square root. R has to be 0. Okay, so there's one solution. If r minus 3 equals 0, add 3 to both sides, r equals 3. And if r plus 2 equals 0, subtract 2 from both sides, and r equals negative 2. So I have 3 intercepts here. When one is at the origin, well, we already knew that. We found that over here when we were looking at the p-intercept, right? Also, when r is 3, p is 0. We have another intercept there, and we have a third horizontal intercept at negative 2, 0. Okay? All right. Let's also review long-run behavior of polynomials. Recall that the long-run behavior of a polynomial will resemble the behavior of the leading term, right? So here we have a polynomial that's in its factored form. Now we could multiply all that out it would be a big job, right? We could do that to see what the actual leading term was, but we really don't need to do that. We don't, because all we care about is the degree of the leading term and whether it's positive or negative, right? The degree of the leading term tells us if the end behavior is going to be like an odd function or an even function, right? Recall odd function end behavior resembles the cubic function, like this. So it goes off to, as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y approaches positive infinity. That's odd degree polynomials, as far as the end behavior goes. And even degree polynomials will resemble the quadratic function, right? There can be all kinds of stuff happening here in the middle, but the end behavior is going to look just like the quadratic function. As x approaches negative infinity, y approaches positive infinity, and x approaches positive infinity, y approaches positive infinity. So all we need to know is the degree of the polynomial, and then of course the sign of the leading coefficient, because it will look like this unless it's being reflected, right? Unless it's being reflected. Well, we've got a negative sign going on here, so we already know that I don't know yet if the degree is even or odd, but whatever it is, I'm going to reflect it. All right. Well, let's see. What would the degree of this polynomial be? All I care about is degrees on the variable here. I can count them up. So this is negative 2t to the first power times t minus 1 squared times t plus 3 to the first power, right, times t plus 2 squared. Well, if I add up the degrees, 1 plus 2 is 3, plus 1 is 4, plus 3 is 7. I know that this leading term is something negative, and I don't know what the value of it is, but I don't care. But the variable is going to have a degree 7 on it. It's going to have a degree 7 on it. So that's all I care about here, is that leading term. That's how it's going to tell me about the end behavior or the long run behavior of this polynomial. Okay, so let's see. T to the 7th, right? That's odd. That's odd. So it means the end behavior is going to resemble the x cubed or the cubic function, right? Except that it's reflected. So the end behavior is going to do this. Anything can be happening in between. We don't know. But we do know that the end behavior will look, or the long run behavior will look like this. The ends of the graphs are going to be are going to resemble the reflected cubic function long run behavior. All right. So then if I were to write this out, I would say as, we're doing f's and t's here instead of x's and y's. So I would say as t approaches negative infinity, f of t, look what's happening to that, it's going up. So f of t approaches positive infinity, right? As t goes to negative infinity, off to the left here, f of t approaches positive infinity, up. And then also, as t approaches positive infinity, right? So as t goes off to the right, f of t is going to approach negative infinity. It's going to go down. Okay, so long-run behavior of polynomials always resembles the long-run behavior of the leading term, right? Of the leading term. If it's an odd degree polynomial, the end behavior goes off to opposite directions. If the leading coefficient is positive, it's going to look just like the cubic function. If it's negative, it's going to be reflected vertically, right? Even degree polynomials will resemble the cubic function if it's reflected. If the leading coefficient is negative and it's reflected, then it would be a reflected end behavior. All right. So with that review, now let's see if we can move into talking about the behavior of graphs near the intercepts. Okay, we know how to find the intercepts, right? We know about the end behavior. Well, there's an interesting characteristic about the behavior of the graph near the horizontal intercepts as well. All right, so here we're looking at, in orange here, and it does keep going, we're looking at the graph of f of x, which is 0.1 times x minus 2 squared times x minus 1 times x minus 4 cubed. Okay, so we can see that the zeros or intercepts of this function occur when all of these factors are set equal to 0, and here they are. There's a horizontal intercept there at x equals negative 2. That is the intercept that correlates to the factor x plus 2, right? We have a horizontal intercept right there at x equals 1. That intercept, it's right over the 1. That intercept correlates to the factor x minus 1. And then we have one more intercept over here at x equals 4. Right? And that intercept correlates to the factor x minus 4. All right. So what do you notice about the graph at each of these zeros? What is it doing? Look, at negative 2, the 0 of negative 2, look how that graph, it comes down, it bounces right off the axis, right? Touches the axis and then heads right back up again. Look at the intercept at 1. The graph crosses right straight over the horizontal axis, right straight over. No hesitation. Boom, right straight over. And look at the intercept at x equals 4, or yeah, x, right back to x. We see that the graph does cross over the axis, right? But it lingers a little bit near, the 0, right? It doesn't cross straight over like it did at x equals 1. It lingers more, right? Do you see a connection between those zeros and the algebraic function? Give you a hint. Take a look at the degrees of those zeros. That's a degree 1 right there, isn't it? Look, when the degree is 2, doesn't that look like the quadratic function right there? The graph just comes down, bounces right off. Looks like part of a quadratic function. When the degree is 1, look at that. That portion of the graph right there at that 0, it looks linear almost, doesn't it? It behaves like a linear function or a degree 1 polynomial. And look here at the 0 of x equals 4. Look how the graph behaves. And look at the exponent on the 0, or the multiplicity, if you will, of the 0. Okay, it's 3. Doesn't that little portion of the graph resemble the cubic function? Interesting, isn't it? In fact, let's generalize that. All polynomial graphs will exhibit this behavior at their intercepts, or at the zeros of the function. If the 0 has a multiplicity of 1, which means the exponent is 1, all right, it's going to cross right straight through, just like the linear function does that has the exponent of 1. If there's a 0 with multiplicity of 2, right, or there's an exponent of 2 on the factor, let's see, like the x plus 2 squared, right? Right, that exponent of 2 tells us that 0 has a multiplicity of 2, or that it occurs twice, right? We can see that the graph looks just like the quadratic function at that 0, okay? With a multiplicity of 3, which one had 3? Let's go back. It was the x minus 4 was cubed, right? X minus 4 to the 3rd power. Look, right near the 0, the graph resembles the cubic function, okay? Now, what do you think would happen if we made these exponents larger? They would just linger a little bit more, right? So what would, say, the graph of, let's say if it had an exponent of 4 or a multiplicity of 4, it would simply linger near that 0 a little bit longer, okay? Just like the quadratic function does when you increase the exponent on there. Here, what if the degree was, say, 5? It would take the same basic shape, but it would linger, just square off just a little bit more, like that. Get close to that 0 and stay there a little bit longer before it went off in the opposite direction. And obviously, the higher we increase these exponents, the more squaring would occur near the 0 and the more lingering. Okay. Now, we're not going to focus a lot on these very high exponents here, but please do know that if the multiplicity is 1 or the exponent is 1 on the factor for the 0, it'll cross right straight through the horizontal axis. If it's a multiplicity 2, it'll bounce off the axis, like the quadratic function. And if there's a multiplicity 3, it'll cross over, but it'll linger a little bit near that axis. All right, so let's talk for a little bit about writing equations for polynomials using the intercepts. Okay, so if a polynomial has intercepts at some values, say x1, x2, all the way up to maybe xn, those are some value, then the polynomial can be written in this factored form. Okay, there will be some stretch factor, a, and then all the zeros will be represented by factors. They will have some multiplicity on them as well. All right. The powers on the factor are going to show us what that graph is going to look like near that 0. We call that the multiplicity of the 0. Okay. The stretch factor we find at the end, that's going to give us, we're going to pick a clear point on the graph to find the stretch factor. All right, let's look at an example. Say we have a polynomial of degree 4. We're going to call it p of x. It has a root of multiplicity 2 at x equals -2. All right, so what does that mean? A multiplicity of 2 at x equals -2. That means that we will have a factor, multiplicity 2, it has degree 2, at x equals -2. So the factor is going to be x plus 2. Why do I say plus 2? Because if I were solving that, I would have to subtract 2 from both sides, and x would equal -2. Right? Now we have another one, a multiplicity of 1 at x equals 0. Right? Okay, so that's kind of like x minus 0, x plus 0, or just x. Right? That has a multiplicity of 1. So I won't put an exponent up there. We don't usually do that. And then there's also multiplicity 1 at x equals 1. All right? The factor that would lead to that 0 of x equal 1 is going to be x minus 1. Right? Because when we solve x minus 1 equals 0, we get 1. All right, there's some stretch factor that we don't know. We want to call this one p of x. All right, now we do know, though, however, that this graph goes through the points with the coordinates 3 and 15. The x coordinate is 3, the y coordinate is 15. All right, so we can use this point now to find the value of our stretch factor, or to find a. I want that value. So let's plug in those x and y values, and let's see if we can solve for a. All right, so we're going to plug, let's see, 15 in for y. Well, p of x is function notation for y. Right? So 15 equals a times, let's see, x is 3. So that's going to be 3 plus 2 squared times 3 times 3 minus 1. Right, so what is that? Let's see, 15 equals a times, let's see, 3 plus 2, that's 5 squared, that's 25 times 3, that's 75 times 2, it's 150. A times 150. All right, solving for a means that I'm going to have to divide both sides by 150. All right, and when I do that, I see that a is 15 over 150, or that's going to reduce down to 1/10. All right, now I've got my function. P of x is going to equal 1/10, or 1 over 10, times x plus 2 squared times x minus 1. Okay? Let's take a look at this graph and see if just the visual of this graph is enough for us to write the formula for that function, or the algebraic representation of that function. All right, and it does keep going. So pull a few arrows there. Okay, so let's see. Let's start with the zeros. We've got one here at x. Ooh, I just did something here. We've got one here at x equals -1. We have another one here at x equals 2. Okay, and we have a third 0 here at x equals 4. All right, so these zeros will correlate to factors. Let's write the factors that correlate with the zeros. All right, well, the first 0 is at x minus 1. The factor that would give us that 0 is x plus 1. Right? X plus 1. And look, the graph comes up, touches the axis, and then just bounces off and comes right back down. Right? So that looks like the behavior of the quadratic function to me, right? So that's going to have an x of 2 on it. So that 0 has a multiplicity of 2. Right? Then we look over here at x equals 2. Okay? That 0 is derived from the factor x minus 2. Okay? And then the behavior of the graph looks like it's resembling the cubic function, right? It lingers a little. It does cross over the horizontal axis, but it's lingering there. So that's telling us that that exponent, or that multiplicity, is going to be 3 or higher. Always go with the smallest. I'm not going to try to ask you to judge how steep or how sharp the squaring is near that 0 to know if it's 3, 5, 7, or 9. Okay? And then this last 0 down here at x equals 4, the graph crosses right straight over. Right? So the factor that leads to the 0 of 4 is x minus 4. And that's just going to have a multiplicity of 1, because look, that resembles the linear function, crossing right straight over. All right, there may or may not be a stretch factor here, but we'll assume that there is. That might be 1, right? So we're just going to say y equals, keep hitting things here with my hand. Okay, so y equals, let me do it up there, a times the rest of all that. All right, so let's see if we can find a clear point that we can use to determine what the stretch factor is, or what that value of a is going to be. I'm looking for a clear point. We don't want to use the zeros. That won't work for us, but here's a nice clear point with whole number and coordinates that looks good for finding the value of a. It has an x coordinate of 3 and a y coordinate of 2. So let's plug those values into our equation. See if we can solve for a. If y is 2, we're going to say 2 equals a times, let's see, x was 3. So 3 plus 1 squared times 3 minus 2 cubed times 3 minus 4. All right. Let's see, solving for a, 2 equals a times, let's see, 3 plus 1, that's 4 squared, that's 16. 16 times 3 minus 2, or 1 cubed, that's still just 16. And then 16 times 2 minus 4, that's -1, so it's going to be -16. So a times -16. Solving for a, we'll just divide both sides by -16. Right, and -2/16 reduces down to -1. So it looks like that's my a. Does it make sense that it's negative? Well, look, what is the degree of this polynomial? 2 plus 3, 5 plus 1, it's 6. That's an even degree polynomial. Long run behavior should resemble the quadratic function, right? It should go off in the same direction because it's an even degree polynomial. They're both heading down, right? So that means it should be reflected or have a negative leading coefficient. So that makes sense. Let's write it now. Y equals -1/8 times x plus 1 squared times x minus 2 cubed times x minus 4. All right, that ends the lecture for section 3.3.